you can find in ordinary dirt that contains so much energy, 2 pounds replaces 6 million pounds of coal. A rock you shouldn't touch with bare hands, controlled more strictly than gold, and determines whether entire cities have power in winter. This is uranium ore, the planet's most controversial geological resource, simultaneously saving us from climate catastrophe and threatening nuclear apocalypse. Let's dive into a world where geology collides with nuclear physics, and ordinary stone can change the fate of civilization. Let's start with what uranium ore actually looks like. If you're picturing something bright green, glowing in the dark like those mutant movies, I hate to break it to you. Most uranium ore looks like regular gray or yellowish-brown rock, sometimes with a greenish tint, sometimes with black spots, but nothing particularly mind-blowing. You could walk right past this stuff in the mountains and never even know it's radioactive. True, there are minerals like uraninite or torbernite that have a brighter yellow-green color, but that's more the exception. Real glow happens, but not from the uranium itself. Some uranium minerals fluoresce under ultraviolet light. They light up bright green or yellow. Geologists use this to find deposits. They shine UV lamps in the dark, and the ore gives itself away with that glow. Looks straight up cosmic, especially in caves, where the walls suddenly burst into neon colors. But the main feature of uranium ore isn't its appearance, it's what's inside. Uranium-238 and uranium-235 are isotopes that slowly decay, releasing radioactive radiation for billions of years now. 1 gram of uranium emits around 12,000 radioactive particles per second. Not enough to kill you instantly, but enough to build up a dangerous dose over years if you constantly carried a rock like that in your pocket. Uranium is found everywhere, in rocks, soil, water, even seawater. The average concentration in Earth's crust is about 3 parts per million. That means in every ton of ordinary dirt, there's roughly 3 grams of uranium. But for industrial mining, you need concentrations at least 100 times higher, from 0.3% and up. Deposits like that are rare and only form under specific geological conditions. The richest deposits are found in Kazakhstan, Canada, Australia, Niger, and Namibia. Kazakhstan leads in production, about 45% of global output. Canadian deposits in the Athabasca Basin contain ore with uranium concentrations up to 20%. That's fantastically high. For comparison, most deposits have between 0.1 and 1%. How do you mine uranium ore? There are 2 main methods: traditional shaft mining and in-situ leaching, which sounds like something from a sci-fi movie but actually works. In the first case, you dig a mine or an open pit, blast the rock with explosives, load it onto dump trucks, and haul it to a processing plant. Just like any other ore, except with radiation. Miners work under special conditions: constant radiation monitoring, dosimeters on every worker, limited time in high radiation zones. The air in the mines can contain radon, a radioactive gas released when uranium decays. It's constantly pumped out by powerful ventilation systems. Without this, miners would receive dangerous radiation doses in a matter of months. Now, about in-situ leaching. Instead of digging a mine, they drill boreholes straight down to the ore deposit at depths of 300 or 600 feet. Through some boreholes, they pump in a solution, usually sulfuric acid with an oxidizer, or soda solution, depending on the type of ore. This solution dissolves the uranium right there underground. Through other boreholes, they pump out the solution that now contains dissolved uranium. At the surface, they extract the uranium from this solution using chemical methods. Underground leaching is cheaper, safer for miners, and less destructive to the environment. You don't have to haul millions of tons of rock to the surface. That's how most uranium is extracted in Kazakhstan. But the method only works for certain types of deposits where the ore sits in porous sandstone that a solution can filter through. After extraction, the ore needs processing. It's crushed, ground up, and also treated with acid or alkali to dissolve the uranium. What you get is a solution containing uranium, along with a bunch of other elements: iron, calcium, sulfur, Rare earth elements. This solution is purified, and the uranium is precipitated as a concentrate called yellow cake. Though it's not always actually yellow, it can be greenish, brown, or black depending on the impurities. Yellow cake. That's uranium oxide with a concentration of about 80% uranium. Looks like a powder or a sintered mass. This is already a concentrated product that gets shipped to the next stage of processing. But it's still natural uranium, a mix of isotopes, where uranium-238 makes up 99.2% and uranium-235 only 0.7%. And for nuclear fuel in most reactors, you need to enrich uranium-235 up to 3 to 5%. Uranium enrichment. That's a separate high-tech industry, wrapped in secrecy and international controls. First, yellow cake gets converted into gas. It's the only uranium compound that easily transitions to a gaseous state under normal conditions. Though normal conditions here means a temperature around 140 degrees Fahrenheit with a slight increase in pressure. Then, this gas is run through thousands of cascades of centrifuges or gas diffusion plants. The centrifuges spin at around 100,000 revolutions per minute, so fast that the outer edge moves at nearly the speed of sound. At this rotation speed, heavier molecules containing uranium-238 concentrate slightly more near the walls, while lighter ones with uranium-235 stay closer to the center. The difference is tiny, which is why thousands of sequential stages are needed. The entire enrichment process takes months and consumes enormous amounts of electricity. A single enrichment facility can use as much power as a medium-sized city. That's why these plants are built next to major power stations or in countries with cheap electricity. And this is where geopolitics comes in. Those same centrifuges can be used to enrich uranium, not to 5% for power plants, but to 90% and beyond for nuclear weapons. That's why the international community tightly controls who gets access to these technologies. The Atomic Energy Agency conducts inspections, verifies that countries are following agreements and not building weapons under the guise of peaceful energy. Enriched uranium gets converted back into solid form, uranium dioxide. From it, they press small cylindrical pellets roughly ½ an inch in diameter and about 2/3 of an inch long. These tiny pellets contain as much energy as half a ton of coal, or around 130 gallons of oil. Hundreds of these pellets get loaded into long metal tubes made of zirconium alloy, fuel rods, and hundreds of rods form a fuel assembly for the reactor. A single modern nuclear reactor, 1 gigawatt of power, holds about 100 tons of uranium fuel. That's enough for 3 to 4 years of operation. During that time, the reactor generates enough electricity to power a city of 1 million people for those entire years, all from 100 tons of uranium. By comparison, a coal plant with the same output burns through roughly 10 million tons of coal over that same period. But there's a dark side. Spent nuclear fuel is the most dangerous waste humanity has ever created. After 3 to 4 years inside a reactor, the fuel becomes saturated with fission products, radioactive isotopes like cesium-137, strontium-90, iodine-131, and many others. Some of them stay radioactive for thousands of years. A single fuel assembly radiates so much that it can kill a person in minutes from just a few feet away. Spent fuel is first stored in water pools right at the plant. The water cools it and shields the radiation. After a few years, once the most active isotopes have decayed a bit, the fuel can be moved to dry storage, thick-walled containers made of concrete and steel. These containers need to last hundreds of thousands of years, until radioactivity drops to safe levels. Where and how to store them that long? A question humanity still doesn't have a good answer to. Some countries reprocess spent fuel, extracting unburned uranium and newly created plutonium, which can be used again. France, the UK, Japan have such facilities. But reprocessing is expensive, complex, and creates additional risks of nuclear materials spreading. The US decided not to reprocess and to simply store spent fuel, waiting for a solution to the problem in the future. Control over the uranium fuel cycle, from mining to disposal, is a matter of national security. Countries with a complete cycle gain energy independence, but also the potential ability to build weapons. That's why the spread of these technologies is tightly controlled by international treaties. The Nuclear Non-Proliferation Treaty recognizes 5 nuclear weapon states and prohibits others from developing nuclear weapons, though it allows peaceful use of atomic energy. But reality is more complicated. India, Pakistan, North Korea built nuclear weapons without signing the treaty or by violating it. Iran is developing a uranium enrichment program, claiming it's for energy, but raising Western suspicions. Israel has nuclear weapons, though it doesn't officially acknowledge it. Uranium ore and the technologies to process it have become tools of global politics. Uranium mining also has environmental consequences. Tailings ponds, massive waste piles left after uranium extraction, contain radioactive elements, heavy metals, and chemical residues. If improperly contained, they contaminate groundwater for decades. There are stories of towns abandoned due to radiation pollution from uranium mining. For example, the city of Melusu in Kyrgyzstan is surrounded by millions of tons of radioactive waste from the Soviet era, which still poses a danger today. But there's another side to this. Nuclear power provides roughly 10% of the world's electricity with virtually zero carbon emissions. In France, nuclear plants generate 70% of the country's electricity, giving it one of the lowest per capita carbon footprints among developed nations. In the context of the climate crisis, nuclear energy is viewed as a necessary component of the transition to a low-carbon economy. How much uranium is left on Earth? Identified reserves stand at around 6 million tons, enough for 1 to 200 years at current consumption rates. But that's only what's already been found and is economically viable to extract. Potentially available resources are far greater, including uranium in seawater. There's roughly 4 billion tons of it there, though extraction is still very expensive. Every year, humanity produces over 360 million tons of plastic. Most of it doesn't disappear. It decomposes over hundreds of years. But what if instead of oil, we could make plastic from sugar? In the very heart of Thailand grows a crop that can change this. Sugarcane isn't just a plant, but a solar biofactory that transforms light into the material of the future. From its sweet juice is born polylactide, a bioplastic that decomposes naturally. How do they create eco-friendly packaging from simple cane that could save the planet? Watch till the end, and you'll discover the secret the industry has been keeping quiet about. Sugarcane is a true biofabricator of solar energy. It belongs to the grass family and is grown mainly in warm, humid regions, such as Thailand, Brazil, or India. In Thailand, particularly in Chiang Mai, cane occupies thousands of hectares and is a key crop for the agricultural economy. Cane isn't grown from seed. It's propagated through cuttings, pieces of stems that have nodes with buds. They're planted in prepared soil, usually in furrows, at a depth of 2 to 4 inches. After a few days, the buds sprout and new shoots begin to form. This plant is very light-loving, so plantations are located in open areas. It needs lots of water, but doesn't like stagnation, so irrigation must be moderate and regular. Over 10 to 14 months, the cane grows to 7 to 14 feet tall. Its stems are thick, juicy, filled with sweet juice. It's in this juice that sucrose is contained, the basis for sugar production. During growth, the cane actively absorbs carbon from the atmosphere, converting it into organic substances. This makes it not only a source of energy, but also a natural absorber of greenhouse gases. Sugarcane is harvested when it reaches maximum sucrose concentration, usually 10 to 14 months after planting. In Thailand, the harvest season falls during the dry period, from December through March, when the plant is no longer growing, but accumulating sweet juice. In many regions of Thailand, manual harvesting is still used. It's hard work performed by experienced workers with machetes. Before this, the plantation is often burned to remove leaves and ease access to the stems. Although this simplifies the process, burning harms the environment, so more and more farmers are switching to green cane. Harvest without fire. Large farms use mechanized combines that cut, clean, and chop the cane right in the field. This is faster, more efficient, and more ecological, though it requires investment. Important: cane residues, bagasse, aren't thrown away. They're used as biofuel, fertilizer, or even for making paper. This is an example of circular economy where nothing is wasted. After harvest, the cane must reach processing as quickly as possible. Otherwise, the sucrose level in the stems begins to drop, and that means quality loss. So logistics here is critically important. Trucks are the most common option in Thailand. Special open platforms or beds with high sides allow transporting large volumes of cane. Buggies or tractors with trailers are often used for short distances, from field to loading point. In some regions where there's appropriate infrastructure, cane is transported by rail cars. This is efficient for large volumes and long distances, but less flexible than motor transport. Water transport is a rare but possible option in areas with canals or rivers. It's used mainly for export or movement between regions. Cane is often not chopped in the field, but transported in whole stems. They're laid horizontally, densely, to minimize losses. At the factory, chopping, pressing, and juice extraction already occur. Large agricultural enterprises use automated loading systems that speed up the process and reduce losses. In smaller ones, work is still done manually or with simple mechanisms. When trucks with sugarcane arrive at the factory, the technological process begins that transforms the green plant into an innovative material, polylactide. This is a complex but fascinating journey where agricultural biomass becomes part of the ecological future. Before the cane enters processing, it's checked for sucrose content. Samples are taken from each batch to determine how suitable it is for production. Then the stems are cleaned of leaves and foreign impurities, manually or mechanically. Then our cane needs to be chopped. For this, the stems pass through mechanical crushers. These are large rollers or rotary machines with sharp blades that cut the stems into small fragments. The goal is to maximally open the cellular structure to ease juice extraction. The chopped cane is pressed in special rollers. Under high pressure, sweet juice rich in sucrose flows out. This juice is collected in reservoirs. The juice undergoes filtration to remove impurities, and then is heated for concentration. Next, a process similar to brewing kvass or yogurt is launched. Special bacteria are added that transform sugar into lactic acid. It's like when microbes turn grape juice into wine. Only here it's not alcohol that comes out, but acid. This process is called fermentation. It occurs in large tanks, bioreactors. There, everything is controlled. Temperature, acidity, how many bacteria are there? So they work properly and don't slack off. Lactic acid is the key ingredient for creating bioplastic. It has properties that allow transforming it into a polymer. The lactic acid is purified and subjected to polymerization, a chemical process in which molecules connect into long chains. The result is polylactide, a thermoplastic polymer that looks like granules or threads. These granules or threads are the basis for producing packaging, tableware, textiles, 3D printing filaments, and other products. Polylactide has high transparency, strength, and heat resistance, making it an ideal substitute for traditional plastic. Polylactide granules are poured into special machines, extruders or thermopresses. There, they're heated to the required temperature until they become a viscous mass. The hot mass is passed through forms or dies. For packaging and bags, the extrusion method is used, that is, pulling hot polymer into long ribbons or film. Cups, containers, spoons, and so on are made by filling corresponding forms with polymer under pressure. To create more complex shapes, like coffee lids, heated film is pressed to the form with a press. As soon as the product is formed, it's quickly cooled. with water, air, or special cooling plates. This is needed so the material hardens and doesn't deform. Finished products are trimmed, polished if needed, checked for quality, and packed for delivery. Before packing, each product undergoes visual inspection or automatic checking for defects, cracks, deformations, irregularities. In large productions, this is done by robotic systems with cameras and sensors. Defective products are often remelted, since polylactide allows reuse without quality loss. After final cooling, polylactide products, still warm from machine touch, set out on their last journey, to the packing line. Here, everything works smoothly. Mechanical arms carefully stack cups in perfect stacks, 50 in each. Product groups are wrapped in biodegradable film or cardboard boxes. Packaging can also be made of polylactide. That is, the product and its wrapper are made from the same material, which simplifies recycling. Afterward, labels are applied with information: polylactide type, production date, batch, disposal instructions. Finished boxes with products are stacked on pallets, wrapped with stretch film, which is often also bio, and sent to warehouses or to customers. Storage temperature is room temperature, but without excessive humidity, so polylactide doesn't start decomposing prematurely. Green packaging is no longer just fashion, but a demand of the times. Videos about plastic harm get millions of views, and brands are looking for alternatives that don't harm the environment. Polylactide from cane is one of the most promising options. After all, cane grows quickly, and the production process doesn't require crazy resources. Your smartphone weighs 5 pounds and holds a charge for 30 minutes. Your laptop's chained to the wall because the battery dies in 20 minutes. Electric cars don't exist. The battery would weigh more than the entire car and only go 50 miles. Cordless power tools, wireless headphones, anything portable, just impossible. All because we never figured out how to mine and refine one soft silvery metal that stores more energy per pound than any other practical battery chemistry. Without this metal, we'd still be stuck with 70s technology. Nickel-cadmium batteries that weigh 10 times more, last 10 times less, and leak toxic heavy metals. Your phone would need a brick-sized battery. Today, we're going inside a facility in Nevada, where this metal is extracted from ancient underground brine. And I'll show you what properties make it irreplaceable and what the world looks like if we have to use something else. The Albemarle lithium facility at Silver Peak, Nevada, sits in a desert valley 190 miles northwest of Las Vegas and has been producing lithium continuously since 1966. 10,000 feet beneath the surface lies a massive geothermal brine reservoir containing dissolved lithium chloride that's been concentrating for millions of years. The facility pumps this brine and processes 6,000 tons of lithium carbonate annually. If lithium had never been discovered, all batteries would use nickel-cadmium or lead-acid chemistry. A lithium-ion battery stores 160 watt-hours per kilogram. Nickel-cadmium stores 40. Lead-acid just 30. To match a modern iPhone battery, you'd need 2.5 pounds of nickel-cadmium instead of 2 ounces. The phone becomes a brick. Mobile computing doesn't exist. The first stage pumps geothermal brine from wells drilled 10,000 feet deep. This brine comes up at 200 degrees Fahrenheit, carrying 300 parts per million of dissolved lithium, along with sodium, potassium, and magnesium. The brine flows into massive evaporation ponds, covering thousands of acres, where the Nevada sun and desert wind do the work. Over 12 to 18 months, the water evaporates, and lithium concentration increases from 300 to 6,000 parts per million. This creates lithium's first critical property. Extreme reactivity makes it the lightest metal that can store electrical charge. Lithium atoms give up electrons more easily than any other practical metal, exactly what you need in a battery anode. Without this, you'd need heavier metals like nickel or cadmium, which means heavier batteries for the same energy. After evaporation, the concentrated brine moves to a chemical plant where it's treated with sodium carbonate to precipitate lithium carbonate as a white powder. This powder is washed, filtered, and dried to 99.5% purity. Lithium carbonate looks like fine white sand, ready to ship to battery manufacturers. Lithium's voltage characteristics become critical here. A lithium-ion cell operates at 3.7 volts. Nickel-cadmium runs at 1.2 volts. To match lithium's voltage, you'd need 3 times as many nickel-cadmium cells wired in series, tripling the weight and complexity. A 6-cell lithium laptop battery would require 18 nickel-cadmium cells. A 1-pound battery pack would weigh 7 pounds, making laptops impossible to carry. Lithium carbonate gets shipped to battery manufacturers, where it's processed into lithium metal or lithium compounds for battery cathodes and anodes. Modern lithium-ion batteries use lithium cobalt oxide or lithium iron phosphate for the cathode and graphite with embedded lithium for the anode. During charging, lithium ions move from the cathode to the anode through the electrolyte. During discharge, they move back, generating current. This reversible movement creates unmatched energy density. A lithium-ion battery handles 1,000 cycles while retaining 80% capacity. Nickel-cadmium manages 500 cycles. Lead-acid gets 300. Without lithium, devices need battery replacement twice as often, generating toxic waste because nickel-cadmium contains poisonous cadmium and lead-acid contains brain-damaging lead. Battery manufacturers shape lithium electrodes into thin sheets and stack them with separators, creating battery cells. Multiple cells connect to form packs for phones, laptops, cars, and tools. Each application demands specific energy density and safety features, but all depend on lithium's unique properties. Lithium's power-to-weight ratio is revolutionary. The Tesla Model 3 has a battery pack weighing 1,000 pounds that stores 75 kilowatt-hours, delivering 300 miles of range. With nickel-cadmium, you'd need 6,000 pounds of batteries to match that energy, but the car weighs only 3,500 pounds total. The battery weighs more than the car. You can't build a practical electric vehicle. Tesla doesn't exist. Electric cars remain a failed experiment from the early 1900s. Every batch of lithium and every battery goes through rigorous safety testing, and there's a specific reason why lithium battery safety standards are so incredibly strict. In 2016, Samsung released the Galaxy Note 7 smartphone with a lithium-ion battery that had a design flaw. The internal structure allowed the positive and negative electrodes to touch under certain conditions, creating a short circuit. Samsung had to recall 2.5 million phones globally. The recall cost them $5.3 billion. Airlines banned the Note 7 on flights. The incident nearly destroyed Samsung's phone business and proved that lithium batteries demand perfect manufacturing with zero tolerance for defects. Today, every lithium battery undergoes crush testing, puncture testing, thermal cycling between -40 and 150 degrees Fahrenheit, overcharging, and internal short-circuit simulation. The rejection rate for lithium battery cells is around 8%. Lithium that's passed all testing gets shipped to electronics manufacturers around the world. The Silver Peak facility produces 6,000 tons annually, but global production is roughly 400,000 tons because demand is massive. Without lithium, portable electronics barely exist. Your phone stays plugged into the wall, like it's the 80s. Laptops are 20-pound luggables with 30-minute battery life. Wireless earbuds, cordless drills, e-bikes, drones, portable medical devices, none of it exists. Anything portable and electronic requires a gas generator or an extension cord. Electric vehicles are impossible. Every automaker tried EVs with lead-acid or nickel metal hydride batteries in the 90s and 2000s. All failed. Maximum range 60 to 80 miles. Batteries died after 2 years. Without lithium-ion, Tesla never gets started. EVs remain a failed technology, and we're stuck with gas cars with no viable alternative. Renewable energy storage doesn't work at practical scale. Solar and wind need massive batteries to store energy when the sun doesn't shine or the wind doesn't blow. Without lithium, these systems would be warehouses full of lead-acid batteries weighing 50 times more, costing 10 times more, needing replacement every 3 years. Grid-scale energy storage is economically impossible. Renewable energy remains tiny because it's too unreliable without storage. Without this lightweight, high-voltage metal, we're stuck in a world where electronics stay plugged into outlets, portable devices don't exist, electric cars are impossible, and renewable energy can't replace fossil fuels. You've seen how brine containing 300 parts per million lithium concentrates through evaporation to 6,000 parts per million. How chemical processing creates 99.5% pure lithium carbonate. How lithium's properties create batteries with 4 times the energy density of alternatives. And why the Galaxy Note 7 proved that lithium production demands absolute precision. If this hooked you, subscribe for more content making modern life possible. Thanks for watching. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean, and that every slab of marble is a frozen story of life, death, and time? Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, It is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges, using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws, or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. Today, I dragged you out to a place where dust isn't a sign of bad housekeeping. It's the smell of serious money and the foundation of everything we call civilization. We're at a cement plant. Look at this landscape. It's like we just landed on Mars, except instead of red sand, everything here is coated in a fine layer of gray powder. Just think about it. We produce over 4 billion tons of this stuff every year. If you tried to stack it all up, you'd get a mountain that would dwarf any skyscraper in New York. We start our journey at the very beginning, the quarry. Just look at these machines. These giant dump trucks look like they escaped from a Transformers movie, but instead of saving the world, they just haul limestone all day long. One wheel on this thing stands about 12 feet tall. That's twice the height of your average pedestrian, who's probably sipping a latte somewhere downtown right now, completely unaware that their apartment is held up by the efforts of these steel monsters. Limestone is the foundation of everything. It's ancient shells and skeletons of sea creatures that decided to die right here millions of years ago, so we could build another shopping mall today. When limestone gets blasted in the quarry, chunks of rock can be the size of a compact car. But for the plant, that's way too coarse. That's where the primary crusher comes in. It's this massive steel jaw that chews through rock as easily as you crunch chips in front of the TV. The noise here is so intense that your noise-canceling headphones would just give up and retire. After the crusher, we get chunks no bigger than 3 or 4 inches. Next, all this mass goes onto a conveyor belt that stretches for miles. It looks like an endless snake crawling through fields and roads straight to the heart of the plant. Now we enter the raw materials prep shop. This is where the cooks of the industrial world mix their secret recipe. Besides limestone, we need clay, sand, and a bit of iron ore. All of this has to be ground into a fine powder called the raw mix. You can't even imagine how precise this ratio has to be. The lab checks the composition every 15 minutes. If they're off by even 1%, your entire skyscraper might just decide it'd rather lie down than stand up. Chemistry rules everything here. It's pure science, where we make molecules dance to our tune. And now brace yourselves, because we're approaching the hottest spot on the map. This is the rotary kiln. If you ever thought summer in Texas was hot, you knew absolutely nothing about life. This kiln is a gigantic steel tube over 600 feet long. It's tilted at a slight angle and constantly rotating. Inside, it's straight up hell. Temperatures in there climb to 2,700 degrees Fahrenheit. That's so hot that iron starts to weep. At this moment, what we call decarbonization happens. The limestone breaks down, releasing carbon dioxide, and transforms into calcium oxide. This is the moment of truth. The raw material begins to melt and clump into little gray balls called clinker. Clinker is basically a semi-finished product, cement in its embryonic state. Just think about the energy needed to keep a fire like that going. They burn everything here, from coal to old car tires. So, here's something wild. Old tires make excellent fuel because they burn completely at these temperatures, leaving behind nothing but energy for our kiln. It's like nature's own brutal recycling program. When this red-hot clinker exits the kiln, it looks like tiny meteorites that just fell from the sky. It needs to be cooled immediately. Massive fans blast it, dropping the temperature from thousands of degrees down to 160 degrees Fahrenheit in just minutes. The whole thing looks incredibly dramatic. Clouds of steam, glowing metal, and that distinctive crackling sound. But this still isn't cement. The final stage is the last grinding. We take our clinker, add a bit of gypsum to it, about 5% of the total weight, and send it into a ball mill. This is another horizontal tube, but inside it's packed with thousands of steel balls. As the tube rotates, these balls drop and pulverize the clinker into such a fine dust that it becomes softer than the flour your grandma uses to bake pies. The gypsum here is needed, so the cement doesn't set instantly when you add water to it. Without gypsum, construction workers simply wouldn't have time to carry a bucket of mix to the wall. This grinding process is incredibly loud and consumes enough electricity to power a small town. But the result is worth it. Now we have a gray powder that can turn into stone on command. We store it in massive silos, these concrete towers that can reach up to 150 feet tall. Each silo holds thousands of tons of finished product. Look at these trucks lined up in queue. They haul this powder all across the country. Rail cars, barges, bags at hardware stores. Cement is everywhere. Every American indirectly consumes close to 1,000 pounds of cement each year. We literally live inside this material. Our roads, bridges, building foundations, even power plant dams. All of it depends on those gray granules we just saw inside that blazing kiln. People often tell me this is a dirty business. And yeah, it's true. There's no cement without dust and fire. But that's where its raw beauty lies. This is an industry that doesn't tolerate weakness. Everything here is massive, everything scorching hot, and everything operates at the physical limits of what materials can handle. It's a real battle between man and matter, where we force solid rock to go liquid, then solid again. But this time in exactly the shape we need. Next time you're walking down a sidewalk or staring up at bridge supports, remember the long journey that stone took. From an explosion in a quarry to 2,700 degrees inside a kiln to steel balls in a grinding mill. It's a long road, packed with chemical transformations and incredible engineering genius. We've learned to control processes that took nature millions of years to create, and we're doing it at a scale of billions of tons. I hope you enjoyed this journey through the world of dust and fire. Personally, I always love seeing how something that looks so simple on the surface turns out to be incredibly complex inside. It reminds us that behind every ordinary thing, there's an entire army of people, machines, and scientific calculations. All right, I'm off to clean the dust off my camera, and you, don't forget to look at the world around you a little more carefully. See you at the next factory, where we'll definitely find something huge, loud, and absolutely fascinating. It's interesting that even in our age of digital technology and artificial intelligence, we're still dependent on a red-hot tube filled with limestone. You can write code for a new app, but you can't live in it. You'll still need a foundation, walls, and a roof. And that's exactly why cement plants aren't going anywhere. They're a reality you can't ignore. It's physics you can't hack. And that's what I love most about it. Here, everything is real. Touch this furnace, you'll get burned. Stand under that clinker stream, you'll get buried. No filters, no fakeness, just pure industrial power. We've traveled a lot of miles today, seen tons of raw materials and giant machinery, and every single time, I can't stop marveling at the scale. Humanity, this weird creature that decided caves weren't enough and started turning mountains into powder to build its own mountains out of glass and concrete. It's ambitious, it's bold, and it's very human. And you know what else is human? Subscribing to my channel right now. All right, that's it. Tour's over for today. The air here's getting too thick, and my lungs are already begging for some clean forest air. But I'm sure tomorrow I'll want to come back to where the big machines work, because that's where you feel the real rhythm of our world. See you. Every year around the world, billions of tons of rock are blasted apart with explosives. Tunnels are carved straight through mountains, and rockets are launched into the sky. But few have ever seen the place where the force capable of reshaping landscapes in seconds is born. Today, we gained access to one of the most tightly guarded industrial facilities, where chemistry, fire, and metal come together to create the legendary TNT, the very substance whose explosive power became the world standard. But the scariest and most fascinating part isn't the explosion itself. It's how this yellow powder makes its journey from an ordinary liquid to a material that can obliterate a house-sized boulder. And trust me, if you stick around until the end, you'll learn a fact about TNT production that will completely change how you see modern industry. TNT, or trinitrotoluene as it's also called, showed up way back in the 18th century when chemists started messing around with toluene. Americans call it TNT, short for trinitrotoluene, and to this day, it's the gold standard. 1 gram of TNT, the unit for measuring explosive force. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant stainless steel vessels, where the temperature holds steady at 400 to 480 degrees Fahrenheit. No, seriously, it's hell in there. 200 to 250 degrees Celsius if you convert it. A mixture of nitric and sulfuric acids gets pumped inside. Concentrates so harsh, they'll melt your gloves right off. The nitration process runs anywhere from 3 hours to several days. First you get mononitrotoluene, then dinitrotoluene, and finally trinitro. The acids circulate in a closed loop. They get recycled instead of just dumping them into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything's under control because the slightest shift and the reaction can go sideways. From the reactor, the mixture heads to coolers, long coiled tubes where the hot TNT crystallizes. Then settling tanks. The heavy TNT sinks to the bottom, while the lighter acids get drained off. That jelly-like mass right there, that's raw TNT, still wet with acid. They wash it with hot water at 150 to 180 degrees Fahrenheit to neutralize what's left. The water drains into the sewage system, and the crystals get dried in vacuum ovens, rotating drums that spin like washing machines. Massive stainless steel vats get pumped full of water at temperatures between 150 and 180 degrees Fahrenheit. The water jets out like in an industrial laundry, washing away residual nitric and sulfuric acid. TNT floats in it like jelly in boiling water, spinning, giving up impurities. The process takes half an hour. The water changes 3 times because the first batch is yellow from acid, the second is cloudy, and the third is already clear as a tear. This water doesn't just go down the drain. It gets neutralized with lime in basins, filtered through a 10-foot thick layer of sand, and then released into the river. Ecology stays under control because acid is poison for fish. Meanwhile, the crystals get unloaded. The mass becomes solid, but still 6 to 10% wet. Now comes the drying, the most interesting part. The entrance to this vacuum oven, a room where 20 rotary drums hum, each about 6 feet in diameter. TNT gets shoveled in there, 200 pounds at a time. The drum seals shut, air pumps out until pressure drops to 100 millimeters of mercury, and heating kicks in, 130 to 140 degrees Fahrenheit. Fans blast hot air through the center. The drum spins at 30 rotations per minute, like a washing machine on spin cycle. Crystals tumble, dry evenly, don't stick to the walls. 2 hours, and the doors swing open. Pure yellow powder, temperature 40 degrees, moisture content 0.5%. A worker in a mask pours it into hoppers, where a conveyor will carry it off to granulation. 5 tons per shift from one drum, and no dust because the vacuum pulls everything into filters. The operator jokes, "Dry as my sense of humor." Without this step, TNT would clump together or detonate from moisture. An hour or two, and we've got pure yellow powder. Color? Light yellow to dark orange, depends on purity. Here we get the top grade, 98% pure product. Next up, granulation. The powder gets moistened, pressed into briquettes the size of a matchbox, then crushed down to granules 2 or 5 thousandths of an inch in diameter. Why granules? Because the powder's easier to pack, doesn't create dust, and detonates evenly. I peer into the press, a giant machine with pistons pushing 200 atmospheres of pressure, and the briquettes come out hard as rock. Then the grinders, hammer mills where the shafts spin at 6,000 revolutions per minute. Dust gets vacuumed out by ventilation, because breathing in TNT, that's gonna cost you. Now packaging. Granules pour into airtight cardboard boxes weighing 100 pounds each. That's the standard for quarries and the military. Every box gets checked for moisture. No more than 0.70%, otherwise the TNT sweats and becomes sensitive. There are also barrel forms for underwater blasts. There the granules get mixed with paraffin so they don't get wet. Boxes are sealed, marked by lot, and done. Off to the warehouse. From here, TNT ships out to quarries, mines, defense. One box is enough to blast through 200 tons of rock. And then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, we're good. Lab techs in masks check purity with a chromatograph. Toluene or acid impurities aren't allowed. Nothing but respect. These people handle explosives like jewelers. Production is massive. 1,000 tons a month, that's millions of pounds. Energy? Electricity from gas turbines, steam from their own boilers. Waste. Acids get regenerated. Toluene gets redistilled. Environment? Filters on a 200-foot smokestack. Wastewater treated until it's clear. Neighbors don't complain. The plant sits 10 miles from the nearest town. Fun fact, TNT doesn't just explode. They melt it at 82 degrees Celsius, 250 Fahrenheit, and pour it into shells like hot wax, or mix it with gunpowder for plastic charges. In quarries, 1 ton can shatter rock the size of a 3-story building. In mining, you can't punch through a mile-long tunnel without it. And in the military, it's the backbone of torpedoes, mines, bombs. You know how much steel came into this plant? Thousands of tons. Reactors made of chrome molybdenum steel, because regular steel just gets eaten alive by acids. I'm standing in the granulation shop right now. Hear that press rumbling? See those granules pouring into bins like golden sand? The air's clean, but it smells like nitrocellulose. Familiar scent if you've ever been to a powder plant. The operator laughs. Don't breathe too deep, or you'll detonate yourself. Joking, obviously. But the discipline? Ironclad. 8-hour shifts. Lunch break with the clatter of spoons on metal trays. Compare that to the old plants. Back then, everything by hand. Women in skirts packing TNT with bare hands. Explosions once a month. Now, robotic arms, sensors, cameras. Evolution. One worker monitors 10 processes from a control panel. And the pay? Competitive. The plant's like a living organism, roaring, churning, producing power. TNT isn't evil, it's a tool. Builds roads, digs mines, defends the country. Without it, no 1,000-foot bridges, no tunnels under mountains. Can metal burn brighter than the sun? Sounds impossible. But one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1,650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder, with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. Without this unassuming rock, often mistaken for ordinary dark pebbles or heavy chunks of granite, modern electronics would instantly collapse into a pile of useless plastic and silicon. Tin ore, or more precisely its primary mineral, cassiterite, is the hidden foundation holding up our entire digital world. When we talk about high-tech, we name-drop gold or complex semiconductors, but this is the invisible glue binding billions of microscopic components into a single working system. Tin's journey begins deep in the planet's crust, where for millions of years, metal-rich solutions seeped into fractures in the earth, forming deposits that today drive the pace of human progress. Cassiterite, often called tinstone, has an incredible density and a distinctive diamond-like luster when fractured, though on the outside, it can look like ordinary brown or black rock. Mining this ore demands massive effort and specialized knowledge. The world's major reserves are concentrated in what's called the Tin Belt, stretching through Southeast Asia, China, Latin America, and Africa. The scale of extraction is staggering in its variety, from colossal open-pit mines and underground shafts to dredging operations on the ocean shelf. For example, off the coast of Indonesia, giant floating dredge factories pull up thousands of tons of tin-bearing sand from the seafloor, sifting it through complex filter systems to separate out the heavy ore particles. The process of transforming rock into pure metal is long and exhausting. Since tin content in ore is now low, the rock first undergoes multi-stage enrichment. It's crushed, washed, and separated using gravity methods that exploit cassiterite's high specific gravity. After obtaining the concentrate, the smelting stage begins in a furnace at around 2,200 degrees Fahrenheit. Here, under the influence of reducing agents, tin separates from oxygen and other impurities, transforming into a liquid silvery metal. But for the electronics industry's needs, this purity isn't enough. The metal goes through a series of refining processes to eliminate the tiniest traces of iron, copper, arsenic, or antimony. Only after this does it become the material we see in the form of solder. Solder. That's the main use for tin in the modern world. It's not just some auxiliary material. It's a critically important component of any electronic device. Previously, soldering used an alloy of tin with lead, but due to environmental requirements and health safety concerns, the world switched to lead-free technologies. Today, the latest circuit boards are joined using alloys where tin makes up 95 or even 99%. Every smartphone, laptop, control unit in cars, or satellite onboard computer contains several thousand soldered connections. Without tin's ability to wet the surfaces of other metals and create reliable electrical contact at low temperatures, mass production of electronics would be impossible. Factories that produce modern electronics operate with incredible precision, and that's where a key tool comes into play. In surface mount assembly shops, specialized machines deposit solder paste through stencils onto circuit boards with accuracy down to the micron. Then the board passes through reflow ovens, where the paste transforms into solid metallic connections. It's an automated process where every second and every milligram of metal matters. If the tin contains even minor foreign impurities, it can lead to microcracks or tin whiskers, thin thread-like crystals that grow from the solder and can cause short circuits. That's exactly why quality requirements for tin ore and purification methods keep getting stricter. The impact of tin on urban development and global energy is hard to overstate. Sure, we don't build house frames from this stuff, but it's in every lighting control system, every elevator, every safety sensor. The growth of smart cities relies entirely on billions of sensors and controllers, each one held together by tin solder. This makes it a critical strategic resource, with entire regions shaping their economic policy around the battle for control over its deposits. Countries with major cassiterite reserves become key players in the high-tech supply chain. But tin ore extraction comes with serious challenges. Deep open pits and seabed dredging reshape ecosystems, demanding strict reclamation standards. Responsible companies try to minimize environmental impact by restoring forests and cleaning water used in the refinement process. At the same time, recycling is playing a bigger role. Tin is a metal that can be cycled back infinitely. Recycling old circuit boards keeps the metal's high purity with way less energy than mining it from ore. This creates a closed-loop economy, where yesterday's shattered screen becomes the source material for a new device. Interesting fact, tin's been used for millennia. When it combined with copper to create bronze, it gave an entire era of human history its name. Back then, tin was hunted down as aggressively as we hunt for oil or gas today. But while ancient people made swords and cookware with it, today it's become a tool for transmitting information. That's the evolution of this metal's role. From the brute force of bronze weapons to the refined precision of a silicon chip, where tin provides the pathway for electrons to flow. The stone once prized for its ability to make copper hard is now valued for its malleability and conductivity in the micro-world. Technological progress demands ever-increasing quantities of this metal. The growth of renewable energy, solar panels, and electric vehicles creates additional demand. Each photovoltaic panel requires tin connections to harvest the sun's energy. Electric vehicles contain significantly more electronic components than internal combustion engine cars, making this element essential in the fight for climate neutrality. Thus, ancient cassiterite becomes fuel for the green revolution. It's crucial to understand that tin deposits are distributed extremely unevenly across the planet. This creates certain risks for global production stability. Any disruptions in ore supply from major mining regions instantly impact consumer technology worldwide. This pushes scientists to search for new methods of enriching even low-grade ores, as well as developing technology for extraction from deeper horizons. Every foot of new mine shaft or every mile of surveyed deposit is a guarantee that factories keep producing new devices, and the planet's digital network continues to expand. The transformation of tin from mountain rock to solder on a circuit board is an example of how humanity has learned to harness the special properties of materials to achieve remarkable results. It's about tin's ability to be the connecting link. When we look at a chunk of tin ore, we see not just a mineral, but the potential for millions of conversations, terabytes of transmitted data, and the operation of complex mechanisms that ensure our comfort. Tin remains a humble yet irreplaceable hero of the industrial stage, working where no one sees it, at the very heart of machines. Production chains that begin in quarries and end in the clean rooms of high-tech factories are testament to our global interdependence. Tin isn't just a detail on a circuit board. It's the backbone of economies across continents. The continuous flow of ore, concentrate, and finished metal is the circulatory system of industry. Every ton of cassiterite pulled from the earth passes through the hands of thousands of specialists before becoming part of our global information infrastructure. And as we move toward even greater automation and digitization, the role of this stone will only grow, proving that great achievements often start with very small but critically important details. So, tin ore is the real key to modernity. It teaches us to value resources that seem invisible, but without them, the world we know would cease to exist. This is a story about how nature gives us materials, and human ingenuity finds the perfect use for them, transforming heavy ore into the lightness of wireless communication and the speed of data processing. Every grain of cassiterite carries its contribution to global development, remaining an eternal reminder that high technology has its roots in the work of the earth, a stone-born origin. From dark depths to gleaming device cases, the journey of tin is the journey of progress itself. A pinch of metal, a few hundred grams per ton of steel. Add it, and the steel gets 30% stronger. Same weight, same thickness. But it takes a third more force to break it. That pipeline under the North Sea, the one carrying gas at thousands of pounds per square inch? Without this metal, the walls would need to be twice as thick. The project, twice as expensive. Nearly 90% of this metal comes from one country, Brazil, and most of it from one single mine. One company digs it up. One family controls that company. They've been sitting on this for over 50 years without most people ever hearing about it. The metal is called niobium, the quietest monopoly on the planet. But before niobium ends up in a bridge or a rocket engine, it starts as something that looks like ordinary dirt. What happens next involves crushing, floating, and a chemical reaction hot enough to melt through most metals. Araxá, small city in Minas Gerais, Brazil. Population around 100,000. Dusty roads, cattle ranches, a rodeo once a year. But underneath it sits the largest niobium deposit ever found. The mine belongs to CBMM, Companhia Brasileira de Metalurgia e Mineração. Private. The Moreira Salles family holds 70%, one of the wealthiest families in South America. They don't chase headlines. They just dig up most of the world's niobium and ship it out. Here's the thing. This isn't OPEC. No cartel, no politics, no sanctions. Just one company sitting on a geological freak. The pyrochlore deposit, a mineral packed with niobium, is so rich at Araxá that nobody else can compete on cost. Canada mines about 7,000 tons a year. Everyone else splits the scraps. Nobody comes close. And the ore they're pulling out of that pit doesn't look like much. Brown rock. Heavy. But inside that rock sits the element that holds modern infrastructure together. Mining starts open pit. Trucks the size of houses haul pyrochlore ore from benches cut into the hillside. Each load, about 200 tons. The ore contains 2.5% niobium pentoxide, 25 pounds of useful metal per ton of dirt. First step, crushing. The rock goes through jaw crushers, cone crushers, and ball mills until it's a fine, wet slurry. Grey, heavy. Then flotation. The slurry gets mixed with water and chemical agents. Air pumps push bubbles through the mixture. Niobium-bearing minerals grab onto those bubbles and float. Everything else sinks. Workers skim the froth. What comes out is a dark concentrate. About 60% niobium pentoxide. From 25 pounds per ton to 600. Just by letting the right particles float. That concentrate still isn't metal. Turning it into something useful takes one of the most violent chemical reactions in industrial metallurgy. Aluminothermy. Sounds academic. Looks like a war zone. Workers load the niobium concentrate into a steel vessel, packed tight with aluminum powder. Then they light it. Not with a match. With a magnesium fuse that burns at over 3,000 degrees. The aluminum rips the oxygen off the niobium. The reaction hits 4,350 degrees Fahrenheit. The whole charge turns liquid in seconds. No external furnace needed. The reaction generates its own heat. Self-sustaining. The molten mass separates. Niobium iron alloy sinks to the bottom. Aluminum oxide slag floats on top. Workers crack the vessel open and pull out a rough ingot of ferroniobium. 60 to 70% niobium, rest iron. Gray. Dense. Heavy as lead. That ingot is worth roughly $40,000 per ton, and most of it will end up inside steel. Now, why does steel need niobium at all? Because of a trick that engineers stumbled onto, and it changed an entire industry. Microalloying. Add 0.03% niobium to molten steel. 0.03%. A teaspoon of salt in a bathtub full of water. When steel cools, its crystal grains grow. Bigger grains mean weaker steel. Niobium atoms lock into the grain boundaries and stop them from growing. Smaller grains. Tighter structure. 30% stronger. Same weight. The Trans-Alaska Pipeline runs niobium steel. So do gas lines under the North Sea. So does every major bridge built in the last 40 years. And there's a reason this matters beyond construction. SpaceX uses a niobium alloy called C103 for rocket engine nozzles. The exhaust bell on the Merlin vacuum engine, niobium. It handles temperatures above 2,500 degrees Fahrenheit without deforming. Survives re-entry heat, engine thrust, and vacuum cycling. No other affordable material does all three. Put a number on it. The global market moves over 80,000 tons of niobium a year, worth roughly $3 billion. Almost all of it flowing through one company in Brazil. But ferroniobium is the commodity product. The real money starts when you need pure niobium. And purifying it requires a machine that melts metal with a beam of electrons in a sealed vacuum. Pure niobium. 99.9%. Not an alloy. The element itself. Getting there means electron beam melting. A vacuum chamber. A focused beam of electrons hits the metal hard enough to push temperature past 4,400 degrees Fahrenheit. Niobium melts at 4,474. Most impurities evaporate before the niobium does. The beam sweeps back and forth, melting the bar top to bottom. Impurities leave as gas. Pure niobium collects as liquid, then solidifies. 2 passes. Sometimes 3. Each one cleans it further. The final ingot glows silver gray. Smooth. Dense. And worth 10 to 20 times more per pound than the ferroniobium alloy. That corrosion resistance is why surgeons put niobium implants inside human bodies. Your bone grows around it, and the metal just sits there. Decades. No reaction. Corrosion resistance is useful, but niobium has another property that makes it irreplaceable for the biggest machines in physics. Nothing protects this supply chain. No strategic reserve. No backup that can scale fast. Canada produces about 7,000 tons a year. Everyone else combined barely registers. If CBMM's Erixa operation shut down tomorrow, a flood, a strike, a political crisis, the world would burn through existing stockpiles in months. Steel mills would feel it first. Pipeline projects stall. Bridge construction slows. Then the specialty markets start fighting for scraps. Aerospace, medical, particle physics, all clawing at the same shrinking pile. And the strangest part? Nobody talks about it. Niobium doesn't show up on the news. Not on sanctions lists. Not weaponized. China has been prospecting for alternatives. A few junior miners in Africa claim deposits. None of them can match CBMM on cost or scale. The Moreira Salles family runs it like a utility. Stable pricing. Long-term contracts. Quiet enough that nobody bothers looking for a way out. That's the genius of it. The quietest monopoly works because it never gives anyone a reason to break it. Niobium. Named after Niobe, daughter of Tantalus in Greek mythology. Discovered in 1801, ignored for a century. Then someone figured out what a few hundred grams of it does to a ton of steel. And the metal went from a curiosity to a dependency. One mine in Brazil, nearly 90% of global supply, makes steel a third stronger with a pinch, stops particles at CERN, powers every MRI scan, survives rocket exhaust at 2,500 degrees, 80,000 tons a year. One family, no headlines. Next time you drive over a bridge, remember, somewhere in that steel, there are atoms from a hole in the ground in central Brazil. And there's only one hole that matters. Coming up, a liquid metal so dangerous that one broken thermometer can evacuate a building. And they still make thousands of tons of it every year. Every year, over 80,000 wind turbines are installed worldwide. But few people know that each one hides a true engineering masterpiece inside. A blade over 300 feet long that can withstand hurricane-force winds and operate for decades. How do you create a structure so light it can be lifted by a crane, yet so strong it won't break even at rotational speeds exceeding 180 miles per hour? From glass and carbon fiber to vacuum resin infusion, the process of manufacturing wind turbine blades resembles precision surgery on a spacecraft scale. Stick around till the end, and you'll discover why these giant wings have become the symbol of a new energy revolution. Modern megawatt-class turbine blades range from 196 feet to 262 feet in length, and for offshore projects can exceed 360 feet. Why such size? A wind generator's power output is directly proportional to the square of blade length. A longer blade captures a larger wind area, increasing efficiency and, consequently, project profitability. However, with increasing size comes a cubic increase in mass. If you simply scale up a blade, its weight becomes unacceptable and gravitational and inertial loads become destructive. So the key challenge is maintaining low weight with colossal strength. To solve the weight problem, American manufacturers have almost completely abandoned traditional metals in favor of advanced composite materials. Fiberglass is the primary material. It's relatively cheap, strong, has excellent fatigue resistance, and provides necessary stiffness. Fiberglass cloth forms the outer shell and most of the internal structure. For the longest and most powerful blades, carbon fiber is indispensable. It's twice as light and several times stronger than fiberglass. It's strategically used in the most heavily loaded zones, in the longitudinal beams called spar caps that run the entire length of the blade and are responsible for its structural integrity. The fibers are impregnated with epoxy or polyester resins, which, when cured, bind the fibers into a single, extremely strong monolith. This is the heart of the process. To create sandwich structures that give the blade volume and stiffness at minimum weight, analogous to honeycombs, lightweight core materials are used, such as balsa wood or specialized polymer foams. Manufacturing a blade is a multi-month process that requires surgical precision, even though it takes place in massive facilities. The first step is creating a giant mold, or matrix. This typically consists of two massive halves made of durable composites or steel. The mold must perfectly replicate the complex aerodynamic profile of the future blade. Profile accuracy is critical for aerodynamic efficiency and noise minimization. Spar caps are essentially the blade's spine. At this stage, strips of carbon fiber or fiberglass are laid down. If the blade is very large, this process is often fully automated. Robotic systems precisely lay fiber layers into special grooves in the mold. This part is the thickest and bears the main bending loads. The next step is laying fiberglass layers that form the blade's outer shell, as well as core material blocks. Fibers are typically laid by hand by experienced technicians, or using automated fiber placement to ensure proper fiber orientation that will resist predicted loads. After laying all the dry layers, the mold is closed and a deep vacuum is created inside. Resin, epoxy, or polyester is introduced into the mold, and vacuum pressure uniformly and completely impregnates all the fibers, displacing air and ensuring maximum density and strength. This process allows manufacturing large, nearly void-free structures with precisely controlled fiber-to-resin ratios. The resin-filled blade is placed in special ovens or left in the mold under climate-controlled conditions. Heat initiates the polymerization process, during which liquid resin transforms into a solid, strong polymer. This process is lengthy and requires constant temperature control along the entire blade length to avoid internal stresses. After curing, the blades are removed from the mold. The two blade halves, upper and lower, are joined together using special adhesive and additional composite layers. This is one of the most complex stages as it requires perfect alignment over dozens of feet. The root section is where the blade attaches to the turbine nacelle. Powerful steel or composite bushings are embedded here that will withstand enormous loads during rotation and transmit torque. After assembly, the blade is sanded and then coated with special protective coatings. These coatings, particularly on the leading edge, are vital for protecting composite material from erosion caused by rain, hail, dust, and insects, which act like sandblasting at high blade tip speeds. American manufacturers like GE Renewable Energy and TPI Composites pay special attention to quality and innovation to guarantee blade reliability for 20 or even 25 years of operation. No blade leaves the factory without thorough inspection. Since internal defects like air pockets or poor resin impregnation can lead to catastrophic failure. Ultrasonic scanning detects internal defects, voids, and composite delamination. Thermography measures thermal signatures to identify areas with varying density, such as defective bonding. Each new blade model undergoes extreme testing in specialized laboratories. The blade is bent to its strength limit, simulating the strongest wind loads and loads from its own weight to ensure it won't break. Then the blade is forcibly bent forward and backward, up and down millions of times, simulating decades of operation to test material fatigue resistance. After manufacturing comes another engineering challenge: logistics. Transporting a blade over 260 feet from the factory, often located in interior US states, to the installation site requires special low-bed semi-trailers that can rotate the blade around corners and lift it to avoid collisions with infrastructure. It's a unique logistical dance that often requires temporary road closures. Transporting blades is a logistical nightmare. Blade length can easily exceed the wingspan of a Boeing 747. To transport such structures on US roads, special extended semi-trailers are used that can lift, rotate, and tilt the blade at intersections and in mountains. This requires temporary road closures, removal of road signs, and even traffic lights. The US continues investing in developing even longer, lighter, and stronger blades, researching thermoplastic materials for better recyclability, and segmented designs to simplify logistics. This ensures that the engineering marvel born in factories will remain a key element in achieving energy security and sustainability. Some blades, especially older ones that have already served their term, instead of being recycled, are buried in specialized landfills in sparsely populated states like Wyoming. Due to their volume and composite material, fiberglass that doesn't decompose, they can occupy significant areas, becoming museums of green energy. The tips of the longest blades can reach rotational speeds of 180 miles per hour. Though they don't exceed the speed of sound, this requires the blade tip to be perfectly designed and protected from erosion. An ordinary raindrop hitting the blade at such speed has destructive force similar to sandblasting. This forces manufacturers to develop high-tech but expensive protective coatings for blade leading edges. Engineers in the US are developing smart blades that can change their shape or have segmented tips. This allows the turbine to adapt to changing wind speeds and thus increase efficiency and reduce loads. Let me show you something incredible. This is a substance that weighs more than lead, gold, or any other metal on the periodic table. We're in Oregon, at a unique facility where they purify and process osmium. It's the 76th element that most people have never heard of in their lives, and that's a real shame. Osmium is like the introvert of the chemistry world. It's so rare and specific that most people simply don't encounter it in everyday life. This is extreme physics at its finest. Ready to see this cosmic stuff with your own eyes? Then let's go inside. First thing they told me walking in, don't touch anything with bare hands. Not because it's expensive, though it's expensive too, but because osmium in certain forms releases a compound that irritates mucous membranes and in sufficient concentration can damage your retina. It's called osmium tetroxide. So everyone here wears gloves, and the ventilation here is more serious than in a hospital wing. Great way to start a tour, right? But I'm already inside, cameras rolling, and there's no backing out now. Wish me luck. Now for the numbers, because without them, I don't understand why anyone would even mess with this stuff. Osmium melts at 5,486 degrees Fahrenheit. It's the highest density of all known elements. A matchbox with a volume of about 3 cubic inches, if you made it entirely from osmium, would weigh around 12 pounds. 12 pounds. That's like a small bag of groceries, only the size of your palm. I held a sample like that once. The feeling's bizarre. Your brain's telling you something this size can't weigh this much, but your hand's absolutely not buying it. It's one of those moments where the number in the textbook and the actual sensation in your palm are two completely different things. Another number worth keeping in mind, osmium's melting point, 5,521 degrees Fahrenheit. It's the third hardest metal after rhenium and tungsten among refractory elements, way higher than steel, which melts somewhere around 2,000 degrees. In practical terms, you can't melt osmium in an ordinary industrial furnace. Period. That's why they don't make ingots here, and they don't cast parts like at a regular metallurgical plant. The whole process takes a different route. More on that in a bit. Where does osmium come from? You don't find it like iron. No quarries or mines. Osmium's a byproduct of processing nickel and copper ore. Deep in the mines of South Africa or Canada, they're extracting nickel ore, and osmium just happens to be present in trace amounts alongside platinum, palladium, and iridium. Concentration, 1 to 10 parts per billion. To get a single pound of osmium, you need to process 500 to 1,000 tons of raw ore. That's why the market price sits between $1,500 and $2,000 per troy ounce. For comparison, gold currently runs just over $2,000 per troy ounce. Osmium is nearly neck and neck with it price-wise. The raw material arrives at this facility as osmium-bearing concentrate, a grayish-black powder packed in sealed stainless steel containers. The containers are small, about the size of a coffee can. Inside might be 2 to 5 troy ounces of material. Each one of these cans represents $3,000 to $10,000 of raw material. They arrive in a regular courier van, but with paperwork running several pages and cargo insurance. The exact amount isn't disclosed publicly, but from the manager's expression, it's clear the figure is substantial. And a small sample taken for incoming analysis. Literally a few milligrams of powder that go into a spectrometer. If the composition doesn't match the documentation, the batch gets returned. No discussion. First purification stage, dissolution. The concentrate goes into a reactor with an acid mixture at around 350 degrees Fahrenheit. Osmium converts to gaseous tetroxide during this process, the very compound they warned me about at the entrance. This gas is immediately captured and absorbed by a specialized solution in a sealed tube system. Zero external leakage. The system gets checked for integrity every morning before startup. Next, chemical reactions convert the osmium back into solid form and store it as what's called osmium sponge, a porous dark powder containing approximately 95% metal. This whole process takes 6 to 10 hours per batch, and there's no rushing it. The reaction proceeds at its own pace, and nobody tries to speed it up. The second stage is hydrogen reduction. The osmium sponge gets placed in a tube furnace, through which hydrogen is passed at a temperature of 1100 degrees Fahrenheit. The hydrogen picks up residual oxygen impurities, and what comes out is metal powder with a purity of 99.9%. This takes another 4 to 6 hours. The tube furnace looks completely ordinary, a metal tube about 3 feet long, hooked up to a gas line. If you didn't know what was happening inside, you'd think someone was just drying laundry. But inside this tube, the powder transforms from a dirty concentrate into one of the purest metals produced commercially in the United States. Stage 3 is pressing and sintering. The powder gets loaded into a steel die and pressed at roughly 3,000 pounds per square inch. You get a small cylinder, about 1 inch in diameter and ½ an inch tall. Looks like a coin, only thicker and darker. Then this cylinder goes into a separate furnace, this time at 2000 degrees Fahrenheit, where the powder particles fuse together into a solid metal. After sintering, the density of the sample is already 22.5 grams per cubic centimeter, very close to the theoretical maximum for this metal. Shrinkage during sintering runs about 15% of the original volume, and you've got to factor that into your calculations ahead of time, because the die has to be created with extra room for exactly that shrinkage. After sintering, each sample is weighed and measured. Weighing here isn't just a formality. The scales are accurate to 1,000th of a gram, because at these metal prices, losing even a few hundredths of a troy ounce is real money. All trimmings, all leftover powder, all fine dust from under the press, collected and returned to the recycling loop. Nothing gets thrown away. Even the wipes used to clean work surfaces go to regeneration. They might contain a few micrograms of metal too. Where does finished osmium go? One application, nibs for premium fountain pens. Osmium is incredibly hard and wear-resistant, so a pen like this can write for decades without noticeable tip wear. That's why you'll see Oz marked on expensive pens next to the manufacturer's name. Another application, electrical contacts in relays and measuring instruments, where you need longevity through millions of cycles, and where ordinary copper or silver wears out faster. And the third area, one they talk about more carefully here, medical implants. Osmium combined with iridium creates an alloy of exceptional hardness, used to make pacemaker components and certain orthopedic devices. The human body barely reacts to this alloy. It's biologically neutral, which in medicine is extremely expensive in the most literal sense. The details of contracts with medical manufacturers, those aren't disclosed here. I asked how much finished metal they produce per month. The answer, 20 to 50 troy ounces. That's 4 to 10 pounds of metal over 30 days of operation. Sounds ridiculously small. But in terms of value, $30,000 to $100,000 monthly from a single facility of this size. And there's a backlog of orders 3 to 4 months out. Demand is steady, supply is limited by nature itself. There won't be more ore, and the number of facilities worldwide that actually know how to handle this metal properly, you can count them on one hand. What do you think will happen when osmium runs out? Drop a comment, because I can't stop thinking about it. But your hand feels something fundamentally different from anything I've held before. Your brain refuses to believe it, but physics doesn't ask permission. That's the whole difference between knowing the number and feeling it in your palm. 12 pounds in your fist, and 0 special effects. We're standing at a modern asphalt plant. It smells like hot tar, heated stone, and a little bit of my morning coffee, which I nearly spilled when I saw the scale of this metal structure. Most people think asphalt is just some black goop they smear on the road, but it's actually a whole science where every pound and every degree matters. We're about to break down this process into parts and see how a pile of rocks and a barrel of sticky liquid turns into a perfectly smooth highway. It all starts at the aggregate storage yard. These are massive mountains of crushed stone and sand you see behind me. This is serious business. The rocks are sorted by size. We've got really fine screenings, and we've got fractions half an inch or even 3/4 of an inch. Why does this matter, you ask? Because asphalt is like a cake. If you put in too many big nuts and not enough flour, it'll just fall apart under your car's wheels. A special loader grabs this crushed stone and dumps it into huge steel bins. Each container holds about 10 or 15 tons of material. Then begins a long journey on a conveyor belt. This rubber track stretches for dozens of feet and carries the stone to the heart of the plant, the dryer drum. Look at this giant metal tube slowly rotating. It's about 30 or 40 feet long. Inside it, a real flame roars. Why do we roast stone? Because there can't be a single drop of moisture in it. If water gets into the hot mix, it'll turn to steam and punch holes in your future asphalt, what we call voids. The temperature inside this drum climbs to 300 or even 350 degrees Fahrenheit. That's way hotter than your oven when you're baking pizza. Once the stone is properly roasted, it becomes super hot and bone dry. Now it needs to be lifted to the very top of the plant. They use an elevator for this, a vertical chain with buckets that stretches up 60 or 70 feet. Up there at the top, the scorching aggregate gets screened again through a set of sieves. It's like a final quality check to make sure no random wrong-sized rock messes up our road. Now we get to the star ingredient, bitumen. That's the same black sticky stuff that holds all the stone together. It's stored in massive vertical tanks that are constantly heated. If the bitumen cools down, it becomes hard as a rock, and we can't do anything with it. Each of these drums can hold up to 20 or 30,000 gallons of this black liquid. The bitumen is fed into the mixer under high pressure. It looks pretty epic, although peeking inside while it's running is a bad idea, unless you want to become part of the road. The actual mixing process happens in a giant mixer. They dump in a precisely measured amount of hot stone, add mineral powder, think of it like cement dust for thickness, and pour in the liquid bitumen. One mixing cycle takes about 40 or 50 seconds. In that short time, the mixer blades have to coat every single grain of sand with a thin layer of black gold. Imagine the responsibility. If you mix it poorly, the asphalt will start crumbling after the first winter. The finished asphalt comes out of the mixer at around 320 degrees Fahrenheit. It's basically molten black lava. From there, it either gets dumped straight into a dump truck bed, or it heads to a storage silo. These silos look like space rockets sitting on a launch pad. They can hold 200 to 300 tons of hot mix for several hours while maintaining temperature. This lets the plant run non-stop, even when trucks get stuck in traffic jams. I'm standing right now at the control panel. People sit here watching every pound of weight and every degree of heat on their monitors. A modern plant is a fully automated system. The operator just enters the recipe, and the computer decides how much sand, how much aggregate, and how much bitumen to mix. This eliminates human error, because a mistake of 0.1% in the formula can cost millions if the road has to be redone a year later. You've probably heard that asphalt is one of the most recyclable materials in the world, and it's true. This plant has a special unit for adding old asphalt that's been milled off other roads. They grind it up and put it back to work. It's awesome because we're not just tossing old rocks into a landfill, we're giving them a second life. The recycled material can make up 20 or even 30% of the new mix. That's good news for the environment and for the builder's wallet. Let's just take a quick detour right now and peek at how this goes down. Dawn breaks. The highway's blocked off with orange cones, and there's this thick steam rising from the hot asphalt. Feels like we're on the set of a volcano eruption movie. Our dump truck slowly backs up to the paver. This massive iron-tracked machine worth close to $500,000. The truck bed lifts, and 20 tons of black, steaming mass at 300 degrees Fahrenheit pours straight into the receiving hopper. Inside the paver, powerful augers are at work. Giant screws, just like the one in your meat grinder at home, only 12 feet long. They spread the hot mix evenly across the entire width of the lane. Behind the machine comes the screed plate, which doesn't just level the asphalt. It vibrates with crazy force to compact it initially. The machine leaves behind a perfectly smooth, black-as-night carpet, but it's still too soft. Step on it now, and your shoe stays there forever. And that's when the heavyweights enter the scene. The rollers. First comes the vibratory roller, weighing about 10 or 12 tons. Its steel drums rotate while simultaneously pounding the road at a rate of 40 or 50 strikes per second. You feel this vibration even through the soles of your sneakers from 30 feet away. This is necessary to squeeze out all the air and make the pavement solid. Behind it rolls a pneumatic tire roller on rubber wheels. It smooths the surface, sealing the tiniest pores so water can't get in. One pass after another, and we get a road that'll last 15 or 20 years. Let's go back to the plant. Another interesting point is air cleaning. You see that big box next to the drying drum? That's a baghouse filter. Inside it are hundreds of long fabric bags that capture dust. Only clean water vapor goes into the air, and all the dust is collected and goes back into the asphalt. So stories about these plants being super dirty, that's ancient history. Modern production is cleaner than the kitchen in most fast food restaurants. Now about volumes. A mid-sized plant like this can put out around 240 tons of asphalt per hour. Just to put this in perspective, that's roughly 12 big rigs worth of material. In a single 10-hour shift, this metal giant produces enough asphalt to lay several miles of new 2-lane highway. That's insane speed and massive responsibility. When a dump truck pulls up under the hopper, about 20 tons of smoking black mass pours onto it. Then the driver covers the bed with a special top so the asphalt doesn't cool down on its way to the paving site. If the temperature drops below 250 degrees Fahrenheit before it gets rolled out, you won't get a quality road. So logistics here is a real race against time. Watching one of these plants operate is like watching a really big, really complicated food processor. Nothing here is wasted. Every motor and every sensor performs its exact function. And while from the outside it looks like a pile of smoking, rumbling metal, it's actually a triumph of precision and engineering calculation. Every mile of highway we drive on vacation or to work started right here, in this hot, noisy place. Stick with me. We've got plenty more fascinating machinery and weird mechanisms coming up that make our lives more comfortable, even if we usually don't notice them. Every year, the world mines over 900,000 tons of rare earth metals. Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born. Baiyun Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth. Lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Baiyun Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Baiyun Obo has become the heart of China's strategy that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, About 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few percent, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact. Just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Bautu area, near Bayonobo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that, over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures, implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Bayoun Obo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels. All of this requires metals extracted from places like Bayoun Obo, and the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Bayoun Obo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure, conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time, most mysterious rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Bayun Obo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Bayun Obo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Bayun Obo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Bayun Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where Earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centers, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels, or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and zero defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. Every year, the world builds hundreds of miles of underground tunnels, but almost nobody thinks about what's holding them up above our heads. Picture this: thousands of concrete segments, each weighing several tons, assembled with precision down to the millimeter, forming tunnels where trains blast through at dozens of miles per hour. Now here's the big question: what happens if even one of them is made wrong? Today, we're diving into the place where the backbone of the subway is born, where one tiny mistake can cost millions or more. But there's a detail they usually don't show. Stick around till the end, and you'll find out what's actually hidden inside these concrete rings. Let's start with what a tunnel lining segment is, and why we need it. When a tunnel boring machine grinds its way through soil, you've got to shore up the tunnel walls right behind it, because soil isn't rock and won't hold itself up. The shield pushes forward, and behind it, installers assemble a ring from several segments, usually 5 to 8 pieces plus one keystone. The assembled ring is what you see when you're riding the subway and looking out the window. Uniform concrete sections with bolted connections along the seams. Looks mundane. Actually, an engineering solution refined over more than 150 years. The plant I visited manufactures tunnel segments for the city subway. Tunnel diameter, 21 feet. Each ring consists of 6 segments and 1 keystone. Width of one ring along the tunnel axis, 5 feet. Concrete wall thickness, 18 inches. One segment weighs close to 4,500 pounds. Monthly, the plant ships out about 600 rings, meaning over 4,000 segments. The math comes out monumental. It all starts with rebar cages. This is the exact moment when steel rods transform into a 3-dimensional structure that'll end up inside concrete and keep it from cracking under load. The rods get cut and bent on automated lines. The machine receives a program, selects the right wire diameter, bends it at the specified angle, and cuts it to size. The thinnest rods here are about 1/4 inch in diameter, the thickest around 1 inch. Then the cages are assembled by hand or welding. It's tedious and monotonous, and workers here are clearly grateful when automation handles the whole process. The finished cage gets placed into a steel mold. The mold is probably the most expensive thing in these entire factories after the presses themselves. It's manufactured for a specific project and specific tunnel diameter. One mold costs anywhere from $200,000 to $400,000, depending on the complexity of the geometry, and it's rated for several thousand cycles. Before each pour, the mold gets cleaned of leftovers from the previous cycle and coated with special release compound. Without it, concrete bonds to the steel permanently, and you can't pull the segment out without damage. The lubing process is its own science. Too much creates pores on the concrete surface, too little ruins the mold and wrecks the piece. Seems minor, but at the plant, they train people separately just for this. Next, concrete. They don't pour regular batch plant mix here. Segments get made from special grade concrete with precisely dialed in water cement ratios, aggregate size, and additives. Compressive strength, not less than 6,000 pounds per square inch. For comparison, concrete in typical residential construction runs around 3,000. This stuff is twice as dense and heavy. Additives in the mix ensure waterproofing, because subway tunnels run below the water table, and the concrete has to hold water back completely, not soak it up like a sponge. The mix is prepared in an automated plant right at the factory and delivered to the form by transport conveyor or buckets. They don't pour the entire form at once. They do it in layers with vibration in between. Vibrators plunge into the concrete, and when switched on, the vibrator squeezes out air bubbles from the mix. If you leave air in, the concrete will have voids, and porous concrete lets water through and is less strong. One segment takes anywhere from 45 minutes to an hour, accounting for all the layers and vibration. Rushing here is harmful. This is one of those cases where slower actually means better. The filled form heads into a heat treatment chamber. Steam curing, that's what it's called. The temperature inside, around 100 degrees Fahrenheit, humidity high. The goal, speed up cement hydration and let the concrete gain sufficient initial strength in 8 to 10 hours, instead of the standard 28 days. After curing, the concrete has about 70% of its design strength, enough to remove the formwork without risk of damaging the product. Demolding, the moment I hold my breath a little every time. The crane operator lifts the top part of the mold, then the side panels swing away, and the segment stands on its own. A concrete arc that was just a sloppy mix 8 hours ago. Looks solid. No wonder. 14,000 pounds of solid concrete with rebar in the center. Next, the segment gets moved by crane to a curing rack, where it'll sit for another 7 to 14 days, until it reaches full design strength. Quality control runs parallel to all this. And it's serious here, because tunnel segments aren't paving stones. Each piece gets marked and assigned a unique identification number. During the pour, they pull test cubes, small concrete cubes measuring 4 by 4 inches, that later get crushed in a press to measure the actual strength of the batch. At the same time, ultrasonic testing of finished segments. The ultrasonic device presses against the surface and measures the speed of the wave passing through the concrete. Dense, uniform concrete gives one reading, concrete with hidden cracks or voids, another. The difference shows up immediately, and that segment gets rejected. Another type of control is geometric. Each segment gets placed on a measurement stand, and all key dimensions get checked. Arc length, thickness, bolt hole positions, surface flatness. Bolt hole tolerance can't exceed 1/32 of an inch. Segments that fall outside tolerances, and it happens more often than manufacturers are willing to admit publicly, either get sent back for rework or scrapped. On large projects, the rejection rate can run anywhere from 1 to 3% of total output. Doesn't sound like much at first, but when a single segment runs $4,000 to $6,000, it adds up fast. A separate curiosity, the waterproofing profile. Around the perimeter of each segment, there's a special groove. A rubber gasket fits in there. When the segments get compressed by bolts into a ring, the rubber deforms and hermetically seals the joint. This rubber profile looks like an ordinary black strip, gets manufactured from a highly specific compound based on chloroprene rubber, withstands pressure up to 120 pounds per square inch, and lasts as long as the tunnel itself, meaning it's designed for a minimum of 100 years. Rubber that'll outlive you and me both. Bit philosophical. Shipping from the factory isn't exactly simple either. The segments are heavy, fragile around the edges, and demand careful handling. They're loaded onto specialized frames, secured with tie-downs, and a flatbed truck hauls them to the construction site. There are limits on stacking height, no more than 3 tiers, because the bottom segments can't take excessive weight from above. At the construction site, they dig a vertical shaft. The segments get lowered underground and assembled into rings right behind the shield as it pushes forward. The shield advances 5 feet, the width of 1 ring, and the crew installs the next one. This rhythm never stops, day or night. I step out of the plant and stop beside a stack of finished segments. Gray, slightly rough, smelling of cement. Totally unremarkable. In a few weeks, they'll be 50 feet below city streets, just sitting there. As long as the city stands. No days off, no maintenance, no attention whatsoever from the people above them. That's the fate of a concrete arc weighing 4,000 pounds. I'd complain, but the concrete doesn't seem to mind. See you on the next tour. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead-built aqueducts adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron, or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it. never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water-repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Every single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, especially wealthy countries in Europe, America, and Japan, got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, "Enough." Imagine a huge meeting of Chinese officials where the decision rang out: "We're done accepting other people's trash." They called this policy, very characteristically, National Sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, "That's it, take it all back. My garage is full and I'm sick of this." And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Of course not, but the panic was massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic, a hunger for waste paper, a hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, there are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, they started implementing mandatory waste separation. Imagine, now you don't just throw out trash, you have to divide it into 4, sometimes 5 different categories: wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle, that's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself, to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems, educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom. Every year, billions of bolts get manufactured worldwide, so many that you could wrap them around the Earth thousands of times. But hidden in that ocean of metal, there are a select few that cost hundreds of dollars apiece, and literally have lives depending on them. Today, I'm taking you to a place where an ordinary bolt transforms into something far greater. A component that withstands extreme temperatures, crushing pressure, and even the vacuum of space. There's no factory noise here, but there is something else. Something they don't talk about openly. And if you stick around till the end, you'll understand why a $500 price tag is just the tip of the iceberg. The first thing that hits you right when you walk in? Silence. For some reason, I was expecting noise, like you'd get in a regular machine shop. But here, everything's calm. A few machines, 3 or 4 operators, and this feeling like you didn't just walk into a factory, you walked into a lab. Actually, that's exactly what it is. A lab. That also happens to be a factory. Let me walk you through how every bolt begins. The raw material is a specific nickel-chromium alloy that has to be ordered ahead of time and arrives in rods about 3/4 of an inch in diameter. One of those rods weighs around 20 pounds. It costs roughly $250, and that's before anyone's even touched it. The material isn't chosen randomly. It can withstand temperatures up to 2,000 degrees Fahrenheit, won't deform under pressure of 150,000 pounds per square inch. And here's the kicker. It doesn't lose toughness, meaning it won't go brittle like glass. A regular semi rumbles down the highway. Nothing special, no markings whatsoever. Thousands just like it roll through Connecticut every day. Inside, on wooden pallets bound with metal straps, lie the rods. Not dumped in a heap, not just thrown together, each layer separated by wooden spacers so the rods don't touch or scratch each other. Because a scratch on the raw material surface is already a detected defect that later gets damaged or cut away. One pallet, typically 40 to 60 rods, depending on length. A pallet like that weighs around 1,200 pounds. The truck can carry 6 to 8 of these pallets, meaning one trip hauls roughly $80,000 worth of material. Yet the truck itself looks no different from one hauling pens to a supermarket. At the factory, the truck backs into the loading dock, a small bay with a single door, sized specifically for one trailer. The driver backs up, the dock locks click into place, and then the forklift takes over. The operator grabs the pallet, hauls it to the raw material warehouse, a separate room with controlled temperature and humidity, because the alloy can't pick up moisture before processing. There, each pallet gets a paper tag with the batch number, delivery date, and material certificate, a document from the supplier listing the exact chemical composition of that specific melt. Without that certificate, the bars don't even make it into the plant. The driver can wait at the gate all day. And this is where things get interesting. The stuff you don't see from the outside. Before a bar hits the machine, they cut off a small chunk, about an inch long, and send it to the in-house lab for incoming inspection. They check hardness, examine the structure under a microscope, sometimes run a spectral analysis. Takes 2 to 4 hours. Only after the lab gives the green light does the batch get accepted and move into production. If the result doesn't match the certificate, they return everything, even if the difference is minimal. They cut a blank from the bar stock. A CNC machine removes material layer by layer. One blank is roughly 4 inches long. Cutting takes about 20 minutes per piece, and during that time, the machine makes approximately 2,000 individual movements with different tools. The chips that remain get collected. They're worth money too. Next, heat treatment. The blank goes into a furnace and holds at 1750 degrees Fahrenheit for 4 hours. This is what's called annealing, a process that relieves internal stress in the metal that built up during cutting. Skip this step and the bolt can have micro cracks invisible to the naked eye, but under load, they become a big problem. After the furnace, the blank gets cooled down, not in cold water, not in open air, but in specialized chambers with a controlled atmosphere where the temperature drops at a rate of 50 degrees per hour. The entire cooling cycle? That's another 8 hours. Now here's where it gets interesting. Thread cutting. The threads on these bolts aren't standard. They're engineered for a specific application, and in some cases are the customer's own proprietary design. The thread pitch might be, say, 28 threads per inch. That's an extremely fine pitch, ensuring maximum load distributed across the entire length of contact. Thread cutting is done on that same CNC machine, but now with a different tool, a carbide-coated threading tap. Cutting speed here is super low, around 30 revolutions per minute. Nothing gets rushed here. After the threads are cut, every bolt gets checked with a thread gauge. If the gauge goes in with the right amount of force, good. If it's too easy or too tight, the bolt goes back for rework or gets scrapped. If a bolt fails inspection, they don't try to fix it. They just start making a new one. Next up, final mechanical finishing. That's polishing the seating surfaces. Under the bolt head, there's a ring zone about 3/60ths of an inch wide that gets smoothed down to a surface roughness of 2 microinches. That's 50 times thinner than a human hair. For comparison, your average bolt from the hardware store has a roughness anywhere from 100 to 200 microinches, and nobody bats an eye. But here, this zone carries contact stress after the bolt gets tightened, and if it's uneven, microscopic movement can start, fretting as engineers call it, and over time the bolt will loosen. Can you imagine? Such massive work, but it's like jewelry. The coating is a whole separate deal. The entire bolt gets a nickel coating, 1 to 2 thousandths of an inch thick, through electrodeposition. Parts get dunked in a solution bath, and a direct current runs through it. Nickel gradually settles onto the surface in an even layer, about 20 millionths of an inch per year. The whole procedure takes 3 to 6 years, depending on the thickness required. After that, they check it, measuring thickness with an ultrasonic probe at 2 to 4 points across the bolt's surface. If there's more than a 10% deviation anywhere from spec, the bolt goes back for recoating. Now, where do these bolts actually go? Aviation is one of the main buyers, engine and landing gear fasteners. Then there are submersibles, where threaded connections have to handle pressure at depths of several thousand feet without corroding. There are clients from the nuclear industry, and there are a few projects in the space sector the factory doesn't really want to talk about. They just say, limited disclosure contract, and smile. When I asked how many bolts they make per day, the answer surprised me. 20 to 50 pieces. That's it. The factory doesn't chase productivity records, but each bolt passes through an operator's hands at least 7 times during the production cycle, which takes a total of 3 to 5 working days. Some bolts take a week to make, if the customer wants X-ray inspection and fatigue testing on top. That's a separate procedure. They load the bolt cyclically, 100,000 tension and compression cycles, watching for any cracks. I asked one of the operators if this all seemed like overkill for a bolt. He looked at me without much emotion and said, "This isn't a bolt. It's a system component whose failure costs more than our entire factory." Short and to the point. So there's your $500 a piece. And after that tour, I don't think it's expensive anymore. You're the best. Subscribe so you don't miss the next factory. It's gonna be even more interesting. Drop a comment saying where you're from, and maybe next time I'll swing by your state. Every year, over 1,000 giant ships are sent worldwide for scrapping, each weighing up to 50,000 tons and stretching nearly 3 football fields in length. It's like dismantling an entire floating city, with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster is inevitable. But here's the most amazing part. Inside each of these massive vessels hides something that turns scrapping into a real treasure hunt. Workers risk their lives among plasma cutters and toxic fumes to extract these valuables. What exactly are they looking for? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone keeps quiet about? Stay tuned. What you'll learn next will make you look at every ship in port with completely different eyes. Why is ship recycling so important? Vessels that we typically imagine as enormous floating megastructures can be nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for sea travel and cargo transportation. But beyond their massive dimensions, these ships have extremely complex internal structures. Hundreds of feet of cables, pipelines, shafts, and various safety and comfort systems, plus countless different elements and mechanisms that perform different functions. This entire architecture isn't just scrap metal, but a complex organism that must be very carefully and properly dismantled when the ship reaches the end of its service life. It's critically important to properly remove all hazardous substances from the vessel that may have accumulated during its operation. These can be bioactive substances, toxic paints, fuel residues, lubricants, chemicals that, if handled improperly, can contaminate the sea, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a natural disaster. However, scrapping these maritime giants also has a very bright positive side. The metal from which the ship is made is excellent and valuable raw material that can be recycled and returned to production. This metal is used for building houses, machines, construction structures, and also for creating new vessels. This way, it's possible to reduce the need for smelting new steel, save energy and resources, and also reduce the amount of waste. Metal recycling from ships becomes an important link in the closed loop of modern industrial economy. Scrapping such huge objects also makes it possible to free up ports where old ships are standing, so new, modern vessels can take their place. This allows optimizing the work of naval bases and promotes fleet renewal. Additionally, proper recycling helps reduce operational costs for maintaining old ships and improves environmental standards in the maritime industry overall. The ship is delivered to special ship graveyards. These are usually coastlines with shallow water or special slipways. These locations aren't chosen randomly. Shallow water coastlines allow easy approach of the ship to shore, where it can be safely moored and dismantling can begin. Often these are small bays or beaches where the giant vessel is specially brought, so it doesn't interfere with maritime traffic and doesn't damage port infrastructure. Slipways, in turn, are large platforms or special structures where the ship is placed for dismantling on land. They're equipped with everything necessary for convenient and safe work: crane equipment, metal cutting tools, waste removal systems. One of the main tasks for specialists is ensuring environmental safety. After all, during operation, the ship accumulated many substances that, if handled carelessly, can harm the environment. These can be not only lubricants and fuel residues, but also toxic paints or chemicals. Therefore, the entire dismantling process begins with removing all such substances. Fuels and lubricants are drained into special containers and taken away for recycling or disposal to avoid getting into water or soil. Similarly with electronics and furniture, everything that could potentially harm nature is removed as a priority. This stage requires speed and maximum caution so that environmental standards aren't violated. After the ship is cleared of all hazardous and household items, the direct dismantling of the hull begins. And this is the most complex and dangerous part. Using special plasma cutters and gas torches, large steel structures begin to be cut into small pieces. This involves both hand equipment and heavy machinery, cranes, lifts, special manipulators. Plasma cutting allows very precise, fast and efficient metal division that will later go for remelting. The dismantling process itself happens sequentially, stage by stage, starting with the most hard-to-reach or dangerous zones. Metal sheets, beams, decks, and internal partitions are carefully separated so as not to damage structures that might still be needed for analysis or recycling. The complexity is that giant elements are often unevenly distributed and may be under tension, and due to corrosion or hull deformation, some parts can unexpectedly drop or fall at any moment. It's also important to emphasize worker safety. During plasma cutting, hot sparks and toxic fumes arise, requiring special protection from workers, respirators, special clothing, and constant air monitoring. A small mistake or neglect of rules can lead to serious injuries and accidents. Therefore, at every step, the process is regulated by strict safety rules, and the entire site is covered by fire suppression systems and medical support. Dismantling the hull and main steel structures of the ship is, without doubt, an extremely important and complex stage of scrapping a giant vessel. However, after this large body of work is completed, the job doesn't end. Ahead lies another massive phase that requires no less attention and certain skill, as it concerns dismantling and sorting countless smaller, but no less valuable and complex materials. One of the most massive and complex processes is working with cables. The ship contains hundreds of miles of cable networks that provide power and communication between all systems. These are powerful steel cables with insulation made of plastic, rubber, and possibly using non-ferrous metals. Cables don't just remain at the recycling site, they're carefully removed, processed, and sorted. Separating the metal core from insulation materials makes it possible to send pure copper or aluminum for remelting, and the insulation layer for recycling as raw material for new polymers. Workers must act very carefully not to damage long cable pieces, and also observe safety techniques due to the presence of residual substances or rust. Another important category of materials is insulation materials that line or fill the ship's walls, technical rooms, and pipelines. Insulation is often made from special materials: mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After removing insulation, it's sorted and sent to specialized enterprises where these materials can be recycled or disposed of without harming nature. Working with ventilation systems also requires thoroughness. Ventilation pipes and units that were used for air conditioning and circulation in different parts of the ship are dismantled and cleaned of dust, lubricant residues, or other substances. Metal elements of systems typically undergo quality remelting, and plastics or rubber often become raw materials for new products. Special attention is paid to water supply systems and sanitary installations. On board the ship are complex shut-off mechanisms, pipelines, fittings, mixers, tanks, and other equipment. Pipe parts and equipment are carefully separated, cleaned of sediment, lubricants, and other contaminants to be sent for remelting or appropriate recycling. After all, these materials may contain toxic substances, so their disposal or recycling happens strictly according to regulations. No less important is dismantling equipment from the engine room. There are engines, generators, pump systems, turbines, and other complex machinery that typically has significant weight and contains large amounts of metals, including non-ferrous ones. Such equipment is mainly repaired and reused or dismantled into parts, some of which undergo recycling. In individual cases, engines even go for sale as used spare parts, avoiding becoming scrap metal. Furniture, household appliances, lighting, and other interior items of the ship also aren't just thrown away. They're removed and sorted. Wooden, metal, or plastic parts undergo separate recycling or disposal. In some cases, furniture, if it's in good condition, is sold for reuse, and all paints, varnishes, and certain polymer materials are taken for environmental recycling to reduce pollution. Without this resource, half of humanity would starve, and 99% of people have never even heard of it. I'm standing 2,300 feet underground in a mine that rarely lets cameras inside. Every single day, they set off explosives down here, and the rock is so brittle that one mistake, and the tunnel disappears along with everyone in it in mere seconds. This is potash. Only a handful of facilities worldwide control its extraction, and today, one of them opened its doors to us. To get 1 ton of final product, you need to process 4 tons of raw ore. And how exactly that happens, and what these giants hide behind their metal gates, you'll see by the end of this video. Where do you find it? Deep underground. Very deep. We're talking depths ranging from 1,300 feet to 3,000 feet, sometimes more. It's like descending to the bottom of the Grand Canyon, then going down that same distance again. But how did it end up in Earth's depths? To understand that, we need to take a journey through time, hundreds of millions of years back. In those distant times, where modern potassium salt deposits exist today, there were massive inland seas and ocean bays. These seas were shallow and existed in extremely hot climates, similar to deserts. In these enormous bodies of water, the water constantly evaporated under the scorching sun. When water evaporated, the minerals dissolved in it, like common salt and, well, potash, started settling on the bottom. Think of it like a cup of really salty water you left out in the sun. The water disappears, but the salt stays behind. But on the scale of entire seas, this process took millions of years. Layers of these minerals piled up one after another, forming massive deposits. Eventually, these ancient seas dried up completely, and other rocks accumulated over the salt deposits: clay, sand, limestone. Millions of years of Earth's tectonic activity, continental drift, mountain building, buried these salt layers even deeper below the surface. That's why we find them at depths of thousands of feet. The potash mine itself is a massive, sprawling system of tunnels, stretching for tens, even hundreds of miles. It's an underground city where hundreds of people and giant machines operate. The temperature here is constant, around 75 degrees Fahrenheit, but humidity can be pretty high. And this is where the real challenges and risks begin. These rocks containing potash are called sylvanite. They're brittle, very brittle. One wrong move, one miscalculation, and a collapse can happen. This isn't the kind of work where you can let your guard down. Every miner, every engineer knows the price of a mistake. These are high stakes, with human lives and multi-million-dollar investments on the line. How do they extract potassium? First, massive drilling rigs create blast holes, small openings in the rock. Then they load them with explosives. Yes, actual explosives. And here come more risks. Calculating the amount of explosive, where to place it, timing the detonation. All of this demands tremendous experience and precision. The blast hits, a deep rumble, and tons of rock come crashing down. After the explosion, another set of giants enters the picture: mining machines. These are massive pieces of equipment that look more like tanks with enormous cutting tools. Their job? Collect the blasted rock and load it onto conveyors. Each machine weighs dozens of tons and costs millions of dollars. They run non-stop, slicing through rock and breaking it into smaller chunks. It's incredibly dusty work, which is why ventilation in the mine is a matter of life and death. A constant flow of fresh air keeps workers safe and maintains visibility. And even with that, everything gets coated in a layer of dust. After traveling hundreds, even thousands of feet underground, the potash concentrate, a mixture of potash salt, common salt, and clay, reaches the surface. And this is where the second, equally complex and fascinating part begins: processing. This isn't some dirty mine anymore. It's a massive, roaring plant where chemical processes bubble and boil. Separating the potassium from all the other junk? That's one hell of a challenge. First step, crushing. Giant crushers turn large chunks of rock into tiny bits. You need this so the next processes can work the material more efficiently. Massive hammers that could demolish a car crush rock here just as easily. You could watch this for hours. Mountains of rock transforming into sand. Next up, the crushed material gets mixed with water. Yep, just water. This is called slurry. This slurry passes through special hydrocyclones, these massive cone-shaped machines that use centrifugal force to separate heavier particles from lighter ones. It's like a spin cycle in a washing machine, but for minerals. This gets rid of some of the clay and other light impurities. And here's where it gets really interesting: flotation. This is the heart of the potash enrichment process. Basically, we make potassium salt float while regular salt sinks. Sounds weird, right? But it works. Special reagents are added to large vats of slurry. These are chemicals that stick to the potassium salt, making it hydrophobic, meaning it repels water. Then air is pumped through this mixture, creating millions of tiny bubbles. The potassium salt, which now hates water, sticks to these bubbles and rises to the surface as foam. Regular salt stays at the bottom. This foam that's risen to the surface, that's our valuable potash concentrate. It gets collected, dewatered, and then dried. Drying happens in massive rotating kilns or dryers, where temperatures can hit several hundred degrees Fahrenheit. This removes all the moisture and gives us a pure, dry product. And right here, we've got our final product, potash, ready to be packaged and shipped to farmers around the world. But the process doesn't end there. Because it's not just about extracting potassium, it's about doing it as efficiently and safely as possible. The water used in the flotation process gets cleaned and cycled back into production. The waste left after separating out the potassium, that's just regular salt and clay. They get disposed of responsibly. At some facilities, that regular salt can even be reused. For example, spreading on roads in winter. From 1 ton of ore, we get only about 25% pure potash salt. That means to produce 1 ton of final product, you need to process 4 tons of ore. Picture this. To meet the needs of, say, an entire country in potassium fertilizers, millions of tons of rock must be processed every single year. We're talking massive volumes of work requiring enormous investments in equipment, technology, and safety. Why is this so expensive? And why are there only a handful of facilities in the world doing this? First, investment. Building a mine and plant like this can cost billions of dollars. This isn't something you build in your garage. Second, incredibly complex engineering. We're talking extraction at enormous depths, working with brittle rock formations, precise chemical processes. Third, safety. Every step in this operation involves risks, from mine collapses to handling chemicals at the plant. Companies spend millions training personnel on modern equipment and safety systems. And finally, it's a rare resource. Potash salt isn't found everywhere, and the places where it exists, these are genuine treasures. Did you appreciate this journey into the world of potassium? We've seen how this valuable resource is extracted from deep within the earth, how it's processed, and how it reaches our fields, helping us grow food. This is a story about engineering excellence, about massive machines, about people working in incredibly challenging conditions, and about a vital element without which the modern world would be completely different. And from you, a subscription. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city, and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are 2 main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works: short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, And in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.002 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000 of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots